Hi everyone, hope you all are doing well. Welcome to today's event. This is the 28th meetup of Kaggle Days Meetup Delhi NCR. So for today's event, we have with us Ishan Dutta. He's a weights and biases dev expert, ex NVIDIA intern, and a 3 into Kaggle expert. So the agenda for today is that from 7 p.m. to 7:45 p.m., Ishan will be talking about deep learning experiment tracking using weights and biases. And from 7:45 to 8, we will have the Q&A session where you can ask him all your questions. So yeah, that's about it. So over to you, Ishan.
Yeah, thanks, Ashpreet, for the opportunity. Hello, everyone. I hope you all are having a nice weekend. Thanks for joining in live with us, and we are going to have a really amazing and insane session. I have a lot of things planned, and this entire session, most part of it is going to be hands-on. That is, I'm going to execute the code live. Whatever I'm going to train the models live. Everything is going to be live. Okay, nothing pre-recorded or stuff like that. So let's move in. Okay. So just a couple of things. If my audio is clear, just type in audible in the chat. I will be seeing the chat as well. Okay. Just type in audible. Great. Audio is clear for everyone. Okay. If the screen is visible, type in visible. If the screen is visible to all of you. Yeah. Amazing. So let's begin. The topic that we are going to talk about is deep learning experiment tracking with weights and biases. Okay, so what is weights and biases? What is the meaning of deep experiment tracking? Everything we are going to see in details. A little about me. Presently, I'm a dev expert at Weights and Biases, San Francisco, USA. I'm a Kaggle 3x expert with a silver medal in the competitions. I have secured top 30 ranks across multiple global level hackathons as well. And previously, I worked at NVIDIA, ISC Bangalore, IIT Kanpur, as well as IIT Ropar. I have more than 10,000 followers across all socials. So if you want to reach out to me, you can reach out to me on LinkedIn or Twitter. Okay, my ID is ishandatta0098. So the first question is, what is experiment tracking? Okay, why do we need it? Because most of the things that you can see that, for example, if you are executing a model, you are already generating all the logs. Okay, so why do we need to track these things? You can just check it that okay, if the accuracy is better, we can move ahead. Why do we need to keep a track of what is not working as well? The first thing is experiment tracking is basically a practice of keeping track of important information. We call this important information as metadata about the different experiments. So, what is an experiment? Say you're running a model. If you change the hyperparameters, that is a different experiment. If you are working on a data set, you use a couple of different models, that is a different experiment. Okay, and things like these. These are everything is an experiment that you are different doing different runs, changing hyperparameters, using different model, all of it. So you can actually track, you can keep a record of all these experiments and the metadata about them, and which means that the different models you're using, the hyperparameters that you're using, hyperparameters such as the size of the neural network or the number of epochs you're training for, and things like that. Then if you are using multiple versions of the same data set, multiple versions of the same model, that also you can track, and you can use it for model development as well, good model development. So the question is, how is weights and biases going to help you in this? Okay, so what is weights and biases? Weights and biases is a platform that helps you build models better, faster with experiment tracking. Okay, we are going to see exactly what all these things mean. You can also do database, dataset versioning and model management, all of it on a single platform. Okay, the best feature of weights and biases is that you can integrate it in within 5 lines of code. Okay, in the actual code that you have, just with the 5 lines of code, you're going to integrate the entire experiment tracking thing. Secondly, you can visualize it seamlessly. You can track live metrics, you can have the logs, system statistics, everything, and you can collaborate in real time. That is, you can show others the graphs, you can discuss the bugs and demonstrate the progress of the project that you have. Fine. So when I was talking about the need of experiment tracking, whenever you are training a model, okay, so this is what a typical log looks like. You can see there are different epochs, there are different losses. This is what it typically looks like. If you read on research papers, this is what the tables look like. You can see the backbone. Okay, this is the model, this was the accuracy, and things like that. but this is not really intuitive. Okay, for the person looking at the first time, understanding what is happening over here is very difficult. That's where weights and biases comes into picture. If you use weights and biases with 5 lines of code, this is what it will look like. You can see that even the epochs, the global step that you are using, the validation, everything has been visualized now. You can even have the images and outputs and predictions in the weights and biases dashboard itself. Fine. Next is you can run hyperparameter sweeps. Okay, if you are changing multiple hyperparameters, it's very difficult to keep a track of which hyperparameter you used with which one. So for example, say you're using one GPU, you used a batch size of 32, you used a dropout of 0.3. Okay, then in the second time you are using two GPUs, batch size of 64, dropout of 64. Okay, and think dropout of 0.7 and 5 epochs. Okay, so keeping track of these things all together at one place becomes very difficult. But as you can see, this has been visualized so seamlessly that you can track it really easily how things are happening. You can also add tags to all of your runs. For example, if you have used one GPU, you have used GPU with Google Cloud Platform, you have used two GPUs with batch size 64, we have used 8 GPUs, and things like these. All of this, we are going to generate these graphs live, and that's how we're going to move ahead. Now, as I said, that we are not going to spend a lot of time in PPTs. I'm going to give a demo of all of this with the help of a real live demo with the help of a Kaggle competition. So the competition that we are going to talk about today is called the Jigsaw Multilingual Toxic Comment Classification. It was hosted on Kaggle a year ago, and the objective of the competition was to use TPUs to identify toxic comments across multiple languages. Don't worry if you don't have an understanding of what TPUs are or even what GPUs are. As a matter of fact, I'm going to explain everything step by step. The important thing that you need to know is what is the data set available over here and what are we actually predicting. So in Kaggle, the best thing is that to understand, to look into the data set, you don't really need to make a notebook for that. Okay, a lot of details are already given in the Kaggle platform itself. So if you are in the overview, then you go to the data tab and slightly move downwards, you can see the different data files that are there. The thing is that this same competition was held 2 years ago with just the English data set. Then it was again held a year ago with a multilingual, that is multiple languages are there in the data set. Okay, we're also going to see how to tackle that. So the data set that we are talking about here, the two main things that we want is first is the comment text, that is going to be the feature. Okay, and we have to classify this comment text as toxic or not, for which means if it toxic has a value of 0, it means that the comment is not toxic, that is it's good. But if it's 1, then it means that it is toxic. Okay, you can leave all this metadata as of now because we are topics. Moving to the notebook. See, first of all, let me just show it to you. Before running any of the code, the notebook will be shared with you all. So before running any of the code, you have to take care of a couple of things. First of all, the language must be Python. Okay, there are two options. The accelerator over here, it should be TPU v3-8. I will explain what this particular term means, but usually it's none. When you start a new notebook, you make it to TPU v3-8, and then you can move ahead. Fine. So, what are the contents that we are going to see today? First of all, let's understand that what is a TPU. Okay, and why am I so after that? Let's use TPUs for this and not GPUs. That first of all, TPU stands for tensor processing units. Okay, just like CPU is for central processing, GPU is graphics processing, TPU is tensor processing unit. It was developed by Google, and TPUs are basically hardware accelerators in deep learning tasks. So this is specifically used for deep learning. And for if you want a better understanding of the internal architectures of TPU, you can I have linked it to two different videos. This will be enough to understand how this is working, but I will just put out some key points. As you can see, the name over here is just not just TPU, it's TPU v3-8. What does this term mean? So there were different TPU chips that were developed by Google Brain. One was V2, then there came V3, then the first was V1, then came V2, then came V3. Okay, so the V3, it has a specialty that it has 8 TPU cores. Okay, what is the meaning of cores? For example, you must have heard of CPUs like quad core CPU. It has 4 different CPUs. Okay, octa core CPUs, 8 different cores. Similarly, this particular TPU v3-8 has 8 TPU cores. That is why the letter 8 is over here. The main two units that are there in these TPUs, the first is called as the matrix multiply unit, that is MXU, which learns the matrix multiplications. So you know that everything that is happening in the background of machine learning is through the help of matrices and tensors, as a matter of fact. Okay, so the matrix multiply unit is responsible for multiplying these matrices. Second is the vector processing unit. Okay, so other than multiplying matrices, you do a number of tasks in machine learning. For example, activations, softmax. For all this, you need a vector processing unit. So these TPUs, what makes this TPU much? Why is the TPU much faster? So for example, if you have want to have an idea, uh, if you run the same code that I have given for on a CPU, it might take you even 10 hours to run. Okay, if you run the same code for one epoch on a GPU, it might take you 30 to 50 minutes to run. If you run the same code on a TPU, it can run within 3 minutes per epoch. Okay, that is the speed we are talking about. It's a lot faster than GPUs, and you don't have to make a lot of changes. So how are we achieving this level of speed? First of all, these TPUs V2 and V3, that is version 2 and version 3, use a special type of data type which is called as B float 16. So you might ask that, hey Ishan, I have heard of float 16, but what is B in this? So see, TPUs were actually developed by Google Brain. Okay, so they put the B from the brain to float 16 just to have their name over there. Okay, if that makes sense to you. So what this does is a simple example of floating point numbers. What you can understand it like a 16-bit floating point number takes lesser space than a 32-bit floating point number. But since a 16-bit floating point number is smaller, it executes faster than a 32-bit. What people at Google did is that the they combined the range of 32-bit floating number. Since this is 32 bits, it can store more decimal places. It combined the range of 32 floating bit number with the storage of 16-bit floating number. What does this mean? That you can actually fit more matrices in the memory and thus more matrix multiplications. So when you're using a GPU, you can either use a 32-bit precision or a 16-bit precision. Using a TPU, you're actually using the range of a 32-bit, that is a larger matrix but a smaller storage. These two things, and with the trade-off of precision a bit, help the TPUs to run much more faster than the GPU can ever can. Okay, so the ideal batch size that is provided is 128 data items per TPU core, but the hardware you can use also for 8 data items per TPU core. Okay, the thing is here, firstly, this is supported both by TensorFlow and Pytorch. But in TensorFlow, all of these computations happen internally. But in case of Pytorch, you have to use a different method called as XLA. Okay, so what XLA is called as Accelerated Linear Algebra Compiler. So whatever deep learning frameworks you are using, okay, so you might be using TensorFlow, you might be using Pytorch and any other such framework. These don't run the code directly as it is. Okay, they first convert it into a computation graph and then that is executed. As you can see, it defines the first a computation graph and then it is executed by a processing chip. What is the processing chip that we have in this case? That is the TPU V2 or V3 board, whichever we use, okay, to train the neural network. Similarly, TPU does not run directly on Python code. Okay, you have to determine the computation graph first before it is being converted to the TPU. In case of TensorFlow, this conversion from the TensorFlow graph to the TPU represent, that is the XLA representation, to the TPU machine code happens all internally. You don't have to do anything additional. Okay, but in case of Pytorch, this is still not supported internally, so you have to use another package which is called as Torch XLA for implementing this on your own. Okay. Now, too important, if you have an understanding of a GPU, how to execute deep learning models on GPU, this will be a slightly more easier for you. In case of GPU, if you are running in Pytorch, you have to use this method called optimizer.step in the training loop to step the optimizer. In case of the TPU code, you have to use exam.optimizer_step. Okay, so this is the first change that you have to do from GPU to TPU. Second is, in case of GPU, you use the device equal to CUDA. In case of TPU, you use the device equal to exam.xla_device. We are going to import this exam, don't worry. So what I will do is I will just do a run all, okay, so that all the code cells get executed automatically. That in that way we can actually save up some time for ourselves. Okay, so the first thing that you need to do is Pytorch XLA environment setup. This is not supported by Kaggle as of now. It's not included in the notebook, so you need to install the setup. You have also to install the won't along with this. Fine. Let this setup be executed. Till then, one important thing that I can show it to over you, a couple of things. First of all, the TPU quota. Okay, so on Kaggle, if you have used it, you know that there are certain quota that is provided to you. So as of now, you can see for this particular week, I have used 11 minutes of the TPU out of 30 minutes. Okay, 30 hours. This is the internet. If you turn on the internet, if you have to download, if you have to execute such statements, or if you have to download some models, you can do it along with the code. If you keep it off, then also no worries. In this case, the models have already been downloaded. So if I can show you the data set, so the jigsaw multilingual toxic data set is there. The model BERT based uncased we are going to use. BERT based multilingual uncased we are going to use. I have also the BERT based uncased model if you want to use it. Fine. One important thing that you can check while using a notebook is what is the preferences for the notebook. Okay, in the environment, what is preferences? One is pinned to original environment. In this case, if you are executing this, okay, so say this is for Pytorch, Python 3.8.0. Okay, so this particular notebook has been run originally on 3.8.0. If you pin to the original environment, when someone else runs this notebook, he will be running on Python 3.8.0 only. If you set it to always use latest environment, and at that particular time Python 3.9 has already arrived, so it is going to run the code on 3.9. What you might ask that what is the use of this? See, what happens is from time to time these packages get updated, okay, and some of the parameters might change, some of the terminologies might change, some the names of the parameters might change. So because of that, people might not be able to execute your code completely with a different environment. So it can be a good, if you are going to leave out on a notebook and not going to update it, it's a good practice to keep it to the original environment. So yeah, this our environment has been set up for Torch XLA. The first step with WANB, that is weights and biases, is that you have to connect with your API key. So when you create an account on WANB, then what you have to do is just like a simple package, you have to import WANB. Then you do a wanb.login command. Okay, so this is going to give you a link to wanbai.authorize. This is your this is going to be your unique token. You just copy it and paste it in this and tap and enter. Fine. So it's true. That is from now on, whatever I do, I am connected. This notebook is connected to weights and biases through their API in real time. Okay. Next is import OS. I'm doing in warnb underscore silent equal to true, because there are some additional logs that we don't want over here. We'll be seeing in the weights and biases platform itself. So what is Torch XLA? I had talked about it earlier. Why we are using XLA? Because Pytorch still does not support TPU computations internally on its own. TensorFlow does. So we have to use a special package called as Torch XLA. It is used to be able to use the TPU and Torch image models, that is TIM. Okay. So we import a couple of different libraries, the standard ones, pandas, numpy, random, torch. Okay. TQDM is for the bars, progress bars. Then torch.nn for torch optimizers, large scheduler. Okay, joblib for saving the model. Then from we import transformers, since we are going to use BERT. Okay, and we will see all this. Then from Torch XLA, these are the different packages that you have to work with. I will explain each of these as we move ahead in the code. Okay. The second part is creating a config file. So I have just kept the config pretty simple. I have just kept the max length, training batch size, and epochs equal to 2. Where did I get these configs from? I run through a couple of Kaggle notebooks that were already available for these competitions, and these three were usually the best, giving the best outputs. You can try out with some different models as well, or you can use Optina or any other hyperparameter tuning method. Okay. Then you can set up a wannabe config separately. Wannabe config is going to tell you which particular competition you are working for. You can specify something else also here. And wannabe kernel, this is telling this is my ID. So whenever someone runs this particular kernel, it gets updated that this kernel has been run. Second thing, we set up a seed. What is seed? Seed is basically whenever you are running, whenever I am running this notebook, there are many different environments that I'm using at once. Environments as in we have the operating system, we have numpy is random, we have the torch, pytorch. Okay, so all of this to make sure that whenever someone runs this particular notebook, the output remains almost the same. We have to seed everything. Okay, so you can see the couple of seeds that I have used. Next is preparing the dataset for this particular competition. The dataset of this particular competition, that is this one, is given along with the dataset of the previous competition. Okay, so if you see over here, you can see that this particular file is data from our first competition, that is 2 years ago, and this particular file, dataset file, is from the second competition, that is the 1 year ago one. Okay, the difference between the two is that one is multilingual, one is English language based, and one has if you see the toxic one of these datasets has toxic as a binary classification problem, that is zeros or one. Another dataset has this as a percentage, so it can be 0, 0.85, 0.5, okay, things like that. So it's up to you how you want to do it. You can either convert both of these as per percentages, or you can use a kind of center as like above zero point 0.5 it's toxic, below zero point 0.5 it's not toxic. Through the different runs, I had found out that not binarizing it will give you better results, but in this case, to keep it simple, I have binarized everything. So you have to load the different data sets. This is pretty straightforward. We are going to use the first 200,000 rows for training. Now, if you are familiar with Pytorch, you can understand these things a little more easy. If you are not, I'm going to explain it. See, for Pytorch, there are some couple of standard things that you need to do. Okay, so if you are using a data set in Pytorch, you need to create a data set which has to have three different attributes. The first has to be init, second is the length, and third is the get item. Okay, what is the init? Whatever you are passing into the data set, okay, whatever is the content of the data set should be covered over here. So in this case, if you see, we have two main things: the common text and the toxic, whether it is toxic or not. So here we have, we will pass through, we have in the dataset comment text, we have the targets, the tokenizer that we are going to use, and the max length that we have. Okay, you can also specify the max length directly over here as well, but it's better if you generalize it a bit more. Fine. So yeah, you declare it. Okay, you declare the common text, tokenizer, max length, and targets. Then you have to specify to Pytorch what is the length of the dataset that you're using. Okay, so you can just do a simple length function, length of the self dot comment text. You can also, instead of comment text, you can also use length of self dot targets given. Okay, next is get item. Get item demonstrates how the data is going to be loaded to Pytorch. Okay, so in Pytorch, this is the beauty of Pytorch. You have to actually specify each and everything, how it is going to happen internally. This gives you a better understanding of the code. Okay, so comment text, we are first going to string every line. Okay, why we do this? Sometimes it happens is that some of the sentences in between, they might not be defined as string, or there might be some problem with the string. So it's always a better way to have it as string. This does not cause any problem, and secondly, it helps us with a lot of errors as well. Second thing is that you have to specify the inputs. Okay, what is this inputs? These are the inputs that is going to go to the model that we are going to provide. Okay, so for that we use the tokenizer.encode plus. What is special about encode plus, and why is this not encode? See, encode plus actually gives you the liberty to use two statements at once. So you can see the first statement, we have only common text. If you wanted, we could also have a second statement, but in this case, since we don't, I have specified it as none. We can add special tokens equal to true. We are talking about the CLS and SCP token. We will see how that works. You can specify the max length equal to true, and I have specified the truncation equal to 2. Why is this important, truncation, specifying the max length? We will see. I will give you very detailed examples of why each and every step that we are doing. Okay, then you have to define three things. Okay, so to run a transformer model, sometimes some particular NLP models, sometimes only these input IDs are enough. Okay, based on the model that you're running, based on the task that you have at hand, you can also specify the token type IDs and mask. Then you have to specify the padding length, and this particular part we will come back later when I explain you how this everything is working. Let's directly jump into BERT. Okay, so how many of you have actually worked with transform models at all? Like if you have worked with BERT, just type in BERT in the chat box. Let me see. If you have worked with BERT or any other NLP model, if you have worked with, such as Word2Vec, Glove, okay, you have derived any type of embeddings, just type in whatever you know about. So BERT basically stands for bidirectional encoder representation of transformers. If you know about the transformer architectures, it's well and good. If you don't know, understanding it in details is not the agenda, but I can give you a brief idea. Is that it consists of two parts: an encoder part and a decoder part. The BERT is actually made from the encoder part of it. Okay, how it works, how it was trained, we are going to see now. So BERT is a method of pre-training language representations. How this particularly BERT was trained, okay, and why it is so much better, and why does it give so much better results than the other ones, is that it is deeply bidirectional and it is unsupervised. Okay, what does this mean? First of all, BERT was actually trained on a large text corpus. For example, on Wikipedia, what you do is, in Wikipedia, you have a lot of unlabeled text. Okay, have you seen any data set ever that you go to Wikipedia and the sentences are labeled as, okay, this sentence is positive sentiment, this sentence is negative sentiment? Okay, you don't see things like that. Okay, that's why it is unlabeled data set. And the beauty about unlabeled data set is that it is available in abundance. Okay, everywhere unlabeled data set is present. So BERT was trained on such data sets, first of all. Second of all, We can use this particular tree-trained model, that is BERT, to a number of downstream NLP tasks. What do I mean by downstream NLP tasks? For example, if you have to do sentiment classification, if you have to do question answering, all these come under NLP task. Okay, downstream NLP task. That is, a main model has been trained on a different data set. You use the training of that model, and then you pick up a number of downstreams. That is a number of different tasks that can be derived from that model that is similar to it. Fine. So BERT outperforms other previous methods, that is previous model, because it is unsupervised, deeply bidirectional system. So we saw why it was unsupervised, right? Because the text that is it has been trained on, it is not labeled. Then one question you might have, that Ishan, whenever I train a machine learning model, I always predict something, right? So in this case, what are we predicting then? Because in case of BERT, as I said, it is not labeled. So if we put the text in the model, that's fine enough. But what will the model predict? Fine, what is it going to train on? That's the question we have. Second, if you to understand that better, you have to understand what are the different types of pre-trained representations. Okay, so for example, there are two types of pre-trained representations mainly. First is context free, second is contextual. Okay, what is context free? These models, if you have heard of it, word to vec or glove, these are NLP models. Word to vec or glove, see, the idea behind any of these NLP models, okay, a simple idea is that you have to generate embeddings. Okay, what is the meaning of an embedding? It can be a representation of a text. For example, uh, if you have a text, for example, I am attending a KDM meet right now. Okay, so the word I, it has to be represented by a number, say 103. The word I am attending, so I am can be represented by 104, attending can be represented by 105. Okay, so these representations are actually called embeddings, and the better embeddings the model provides you, the better your model is going to perform. Okay, this is the actual usage of this. So all of these NLP models are going to provide you embeddings. But how good are these embeddings and how are they generated basically? First of all, we have word to vec or glove. Okay, these are context free. What do we mean by context? For example, say you have these two phrases, bank deposit and river bank. Okay, in this first phrase, the word bank actually means a particular building or an entity which is related to the transaction of money. In the second phrase, the word bank is actually the edge of a river. Okay, so you can see that the meaning of bank in both these places is actually different. Okay, the meaning, with the meaning I mean the context. So the context of bank is different over here as compared to here. But the problem with context free pre-trained representations is that it does not consider it. What do I mean? That the representation of bank, let's say bank is embedded to the numerical representation 104. Okay, so for bank deposit it's going to be 104 deposit, and for river bank also it's going to be 104, a river of 104. Okay, that means the meaning for the particular model, the meaning of bank is same in both these phrases, whereas it is vastly different in the real sense. That is why these models are called context free, and these do not perform really well in when generating embeddings, because they have one particular embedding for every word. They do not consider if it's the same meaning or same context as or not. Okay, second we come up to contextual. Okay, which actually consider the different meanings of different words. So contextual is actually classified as unidirectional and bidirectional. Some people also classify it as unidirectional or shallow directional and deeply bidirectional. Okay, what do we mean by unidirectional? See, BERT was basically built upon different models such as semi-supervised sequence learning, generative pre-training, elmo, and unfit. But these all of these models, they were actually unidirectional. What is meant by unidirectional? For example, if you see this sentence, I made a bank deposit. Okay, and you have to represent the word bank in the form of an embedding. So in case of unidirectional, you can only represent it from the left side of it. That is, you can take consider this sentence as, if I just tell you that, hey, the sentence is I made a, and then I give you a blank. Okay, how good is your representation going to be? Or you can use only the right side of it. That is I give you only blank deposit. Okay, so you have to generate the representation based on that. So the unidirectional representation of bank is based on I made a but not deposit. Only the left side of it, you can see that I made a is not, if I just say you that I made a blank, okay, it can be anything. I made a cake, I made a notebook. Okay, it can be anything. It's not enough to generate a good representation for it. That is the main problem with unidirectional contextual representations. Some previous works, they do combine the separate left context and right context together, but it's in a shallow manner. We are going to see what deeply actually means in terms of bank. Now in terms of BERT, Bird represents bank with both its left and right context. Okay, so in the previous case, we were only using I made a. Okay, just this part of it to determine what is the meaning of this word bank. In case of bird, we use the left part of it, that is I made a, as well as the right part of it, that is deposit. So you can see if I give you a sentence like I made a dash deposit, the probability that you come up with the word bank is much more higher. Okay, that is why the model understands the word bank much better as compared to the unidirectional ones. And it starts from the very bottom of the deep neural network. That is why it's called as deeply bidirectional because we are considering both the directions, and deeply because it starts from the very bottom of the deep neural network. Okay, so how is this actually implemented while training bot? For example, the original sentence that you have is the man went to the store, he bought a gallon of milk. Okay, this is the original sentence that you have. The input that you give to bot while training is the man went to the mask 1, he bought a mask 2 of the milk. See, earlier I had raised a question that these unsupervised corpuses like Wikipedia, these are not labeled. Okay, so what is the particular model that we are training from scratch, predicting? Okay, so this is what it is predicting. What we do is we mask out 15% of the words in the input. Okay, what is meant by mask out? The Yeah, what is meant by mask out is that these particular masks are not visible to the model. Okay, so you can just see that the man went to the space. Okay, you can consider it as a blank space. He bought a blank space number 2 of milk. Now it is the job of the model to predict what are the different masks. So the answer over here, that is the label. The label will be mask 1 is store, so that is the man went to the store. Mask 2 is gallon. So the bird was trained like this. It was given such an input set sentence with different masks, and it had to predict, and it had to predict whether this mask, it's the mask that is considering is correct or not. Fine. Second important thing that BERT was while training, it was considered is that to learn relationships between sentences. Why it is important? For example, if you are using some question answering type of systems, okay, so you need to have a very good understanding the relationship between different sentences that were going on. For example, let a sentence A be with there. The man went to the store. Sentence B is there. He bought a gallon of milk. You can see that these two sentences actually come together. That is, it makes sense if I say sentence B after sentence A. That is, the label that we have generated here is next sentence. That is, sentence B is the next sentence to sentence A. Similarly, we can have a different example. The man went to the store and penguins are flightless. You can see that sentence A and sentence B are not connected. So the label here is not next sentence. So along with this, BERT also has to predict whether the particular next sentence is the next sentence for A, and whether the next sentence, that is B, is the next sentence for A. Okay, these are the two important techniques that helped BERT outperform most of the other NLP models. Now, this is what the model looks like. Okay, this is again in Pytorch. So you have to have two important functions whenever you are declaring a model in Pytorch. First is you have to extend the nn.module. So whenever you are declaring models in Pytorch, you have to extend the nl.module package. Okay, so the init function is there. We supply the BERT path over here. So since we have already downloaded the BERT over here, you can see I've added the data set of BERT based multilingual uncased, and the path is already copied. So this is the BERT path we are talking about. Second is self.BERT. This is the original model that we are going to use. Okay, so transformers.BERT model dot from pre-trained. This from pre-trained is important. We are using the pre-trained version because we are performing a downstream NLP task. Okay, and we pass the BERT path to it. So the BERT model from here, multilingual uncased, will be loaded to self.BERT. We add a simple dropout layer with a percentage of 0.3 and a simple output layer. The BERT gives an output of 768. Since we are going to use pooling layers as well, we have multiplied it with 2. Fine. Next, we go to the forward function. What is the usage of this forward function? Just in case of TensorFlow, you declare the model layers one by one. Okay, like nn dot dense, then there is an nn dot there is a if you are using Keras, okay, so Keras dense, then there is a dropout, then again you put up a dense layer. Okay, and you move ahead like that. Similarly, that exact thing is implemented in the forward function in Pytorch. So you can see, first of all, we have to get the outputs from BERT. Okay, three outputs. We provide three inputs to the BERT. As we had seen over here in the BERT dataset that we had generated, it is generating three different inputs to the model. The first is IDs, second is token type IDs, third is the mask. Okay, so these three inputs are provided to the model: IDs, attention mask, and token type IDs. And the BERT gives us two different outputs. We are going to use the first output in this case. So we supply it to the average pooling layer and the max pooling layer. We concatenate the results, we pass it to the dropout layer, and we obtain the output. Fine. So this was the model. If you don't know what are IDs, what is the meant by what is meant by attention mask, what is meant by token type IDs, don't worry. I'm going to explain these things to you as well. So we first declare, we have declared this BERT based uncased model. Okay, we can just put it out over here that MX, or you can do a model equal to BERT based uncased. We pass the BERT path. Okay, this is the BERT path as I had shown all of you. So what are the different model inputs? You can see that there are three different inputs. Okay. Shivam is asking, do we have to manually label? No, you don't have to manually label the data set, Shivam. It actually uses masks automatically. So this is a different, that was when I was talking about, it was how BERT was originally trained. This is a different task that we're at hand here. So first of all, you can see that there are three different inputs. Okay, you will see what these three different inputs are. First is input IDs. Okay, input IDs are often only requirement parameters to pass the model as inputs. Okay, they are the token indices and numerical representations of tokens. If you don't know what is token, no worries. First of all, we have already imported transformers. Okay, we put the tokenizer, BERT tokenizer. See, BERT has a different tokenizer. There are different models like Roberta is there. Roberta has a different tokenizer. Since we are using BERT, we will use the BERT tokenizer. We have it in this variable, and we write a sequence. Sequence is nothing but a sentence, you can say. So a Titan RTX has 24 GB of RAM. Okay, tokenized sequence, that is, we break this particular sequence into different tokens. Okay, so tokens can be words or subwords. Some people think that every word is a token. No, it doesn't happen like that. Only the words that are there in the dictionary of that particular tokenizer are considered as words. For example, a Titan, all these are actually in the vocabulary of this particular tokenizer. But RTX is not a particular word in the vocabulary. So in these cases, it actually divides it the word into subwords. So you can see here RTX became RT and X. What is this meaning of this X? See, the tokens that can then be converted into IDs, and they can be understandable by models. Okay, and you can see here that the tokens are either words or subwords, as I said. Here for instance, VRAM. Okay, so this VRAM also, this is not in the vocabulary. It was differentiated as VR. So VR is actually a vocabulary word, and hash am. So you can see that wasn't in the vocabulary. It has been split as VRAM. Okay, to indicate that these tokens are not separate words. Okay, so VR is actually a vocabulary word, but AM is not a vocabulary word for this particular tokenizer. To indicate that it's not a vocabulary word, we add two hashes to this. Okay, this all of this happens automatically. Okay, you don't have to do it manually. Second is, these tokens can be converted to IDs. Okay, so you can find the first inputs and you just pass the sequence to the tokenizer, and the encoded sequence is saved in this input IDs. Okay, so within input, you can print the encoded sequence, and this is what it looks like. So this particular sentence, a Titan RTX of 24 GB of RAM, okay, has 24 GB of RAM. First, it is converted into different tokens. These are the different tokens that it was converted into, and then the different encodings that we obtained. 101, 143, 143 is for A, 15829 is for Titan, and so on and so forth. It starts from 101 and ends for 102. Okay, yes, 101 and 102 have a special meaning. These are the special tokens we were talking about. 101 is the CLS token, 102 is the SCP token. What is the usage? We will see in the next part. Note is that it adds the special tokens. Okay, now again, if we are going to decode this sentence, just like this particular sentence was encoded in the form of numbers in this particular form, we can again decode it to the original sentence using the tokenizer.decode method. When you decode it, you can see that CLS token has already been added to it, and an SCP token. Okay, CLS was represented by 101 over here. SCP is represented by 102 over here. You can also choose not to add these special tokens, but it has a special purpose, which I'm going to show you. Second important input is that, firstly, you saw that there's input IDs that we are giving. Second important input is attention masks. See, the name of the original transformer paper was attention is all you need. Okay, so that is why this part is very important to understand what the attention mask really is. For example, say you don't have a sequence and independent sequences. You want to combine two sequences together, okay, while training the model. So say you have a sequence A, which is a string which is called as, this is a short sequence. You have a different sequence B, and this is a rather long sequence. Okay, it at least longer than sequence A. So when you encode these, encoding what will be generated, this type of a representation is going to be generated for sequence A, and similar type of representation will be generated for sequence B. When we print it, you can see that A is now represented, this particular sentence is represented like this particular sentence is represented like this. You can see the CLS token and SCP token in both of these. Now the problem is, if you want to combine these together, that is batch these two particular sentences together in one particular tensor, you can't do that. Why you can't do that? If you see the length of the encoded sequence of A and B, these are very different. Okay, one is 8 and one is 19. To put two different tensors together, okay, in one particular tensor, you have to make sure that the length of these two tensors is same. Okay, how do we make that same? It's very simple, addition and subtraction. Either you add 11 to 8, okay, 11 elements in this particular list to make it equal to 19, or you remove 11 elements from sequence B to make it to 8. Okay, now the thing is that if we remove many elements from sequence B, we will be losing a lot of data. So what we choose is we add a number of elements to this. But the question is, hey Ishan, that these many representations are already there, and as I said that every number is actually representing a token, so how can we just add random numbers at the end? We don't add random numbers, that's the solution. We only add zeros. So to add this, we use tokenizers, and you can specify the argument padding equal to true. Okay, padding equal to true, what it will do is based on the maximum length of the sequence that you have. Okay, so in this case, it calculates everything internally. So in this case, the tokenizer knows that sequence B is of length 19, but sequence A is of length 8. So it is going to pad sequence A with 11 zeros. So you can see the zeros. Okay, in previous case, sequence A started at 101, ended at 102. In this case, sequence A started at 101 but ended at 11 zeros. Okay, and sequence B is as it is. Now the length of both sequences is same. Now we can combine them together. Okay, but here is another problem. How is the BERT model going to know which of these letters are actually representing tokens and which of these are simple paddings that we are using? Okay, to know that, we are going to use the attention mask. It's very simple to understand. Wherever the tokens, the numerical representations, okay, can you please repeat why are we padding extra elements? See, when you have to add two particular tensors together, right? Let me just see. What happens is, if you have a tensor like this, okay, if you have a tensor of size 2, if you have another tensor of size 4, okay, you can't combine these two tensors together because it will look something like this. Okay, it's going to look something like this. But this is not possible. Okay, this is wrong because the length of the first row, that is the number of columns in the first row, has to be equal to the number of columns in the second row. So it should either look like this, that is, you remove these two elements from this tensor, or you add two more tensors to it. Okay, so it can look like this. Okay, so in this case, this is sequence A, it has say only two elements. This is sequence B, it has four elements. When you try to combine it together, since it has only two elements and it has four elements, it cannot be combined together. It's mathematically not possible. So either you remove two elements from B, so this is A and B, so B also has the same length of 2, A also has the same length of 2. Okay, but this will cause you data loss. So instead what you do is, in case of A, you add two extra zeros to this. Okay, B is as it is, the rest of elements of A are as it is. You add just two extra zeros. Now the length is equal, and now you can batch these sequences together. But to understand to represent these zeros in the form of, how will the model understand that this number, say 10372, is actually a useful token and this zero is not a useful token? Okay, to understand this, we use the attention mask. Okay, so when you pad these sequences together, you get the attention mask automatically. The ones represent the tokens which are original, that is from 101 to 102, it is everything is represented. That is, you can see 8 ones over here, but you can see 11 zeros over here. Okay, these zeros mean that these particular tokens are not to be used by the model for training. Again, for sequence B, since we had not added any additional zeros for it, we have all ones over here. Okay, so this is how the model knows which part of the sequence, which token to pay attention to. If it is specified to 1 in the attention mask, the model is going to pay attention to that token. If it's going to be 0, it's not going to pay attention. Okay, this is what we mean by attention mask. So just a quick recap: we first generate input tokens. Okay, we have a simple sequence, we generate its encode, we tokenize it in this form, then we generate its encoding. Okay, but if we have to combine two different sequences together, especially having different lengths, then we need to either increase the length of the first sequence or decrease the length of second sequence. Decreasing length is going to cause data loss, so we add So we add an additional zeros to this. But to keep in track of these additionally added zeros, we use the attention mask. One means the letters, the tokens which are actually have some meaning. Zero means the tokens which do not have any meaning. Okay. Next, token type IDs. Three inputs were there. IDs, attention mask, we have already covered. The third input is token type IDs. See, what happens is some models purpose is to do classification on pairs of sentences. Okay, so for example, if we have sequence A, that is Hugging Face is based in New York City, and sequence B, where is Hugging Face based? So if you have to combine these two sentences together, you have to use special tokens. First is the CLS token, and then is the SEP token. So if I encode it, then I again decode it. So it's going to, if we have combined it, you can see I've passed both the sequences together, so it's going to act as one sequence. But we have to keep track of the separation between the two sentences. For example, Hugging Face in based in NYC. This is the answer, and this is the question. I had talked about question answering earlier. This is the question. You have to keep a separation between the answer and the question. So for that, you are using the SEP, that is the separation token. It starts with CLS. The first sentence is there, SEP. Second sentence is there, SEP. Okay. Yeah. What happens? What the token type IDs does that? It's super simple. For the first statement, we represent all the tokens with zeros. Okay. For the second statement, we represent all the tokens with ones. Don't confuse between the attention mask is a different meaning, zeros and ones, and token type IDs has a different meaning. Okay. So zeros represents, you can see the number of zeros, it represents sequence A. So this particular part is represented by zeros. This particular part is represented by ones. Okay. So after passing this token type IDs, now the model very well knows which is the first sentence and which is the second sentence. Okay. This was the three inputs that we are going to feed to the BERT model. If you understood this, you can implement any transformer model that you want. BERT, multilingual BERT, Roberta, XLM Roberta, everything. Okay. Most of the Kaggle computations are going to be simpler for you from now on, because especially the NLP ones. Now coming to weights and biases, the step 2 in weights and biases is going to be that you need to initialize weights and biases with the name of the project. Okay, so we in Pytorch we define the run function. warnb.init is the command that you have to use. You can specify the project that you want to use. I have specified that as Jigsaw TPU v3. The warnb config that we had previously defined is done over here. We do a group XLA. I will talk about it later. Why do we do that? Second is that in this example, we are going to log the training loss, epoch, and ROC AUC score. And to do this, we need to instruct warnb to watch the model. So in this case, we have two loop functions. First is the training loop. Second is the evaluation loop. Both the code is almost same. I will just explain the training loop. You can make out the evaluation loop yourself. Training loop, we are passing the Pytorch data loader, the model, the optimizer, device, and scheduler. By default, it's none. If you don't have a scheduler, you have to specify within the training loop itself that where is the model, what is the model we are talking about. It's simple, model.train. You pass the batches. I've already talked about these inputs that you're providing. You transfer them to the device. In this case, it's a TPU. You do an optimizer.zero grad. You obtain the outputs from the model. You calculate the loss function. Here is the second warnb step, warnb.log. It's that simple. Okay, you just tap in warnb.log. You specify the name of the parameter. You specify the value. Okay, and it will be logged in real time. I'm going to show that to you. You can do a scheduler.step as well. Simply the evaluation loop goes similarly. Okay. Then we have declared the maximum length, training batch size, and epochs. We are going to run it for two different epochs. The tokenizer, we are using the BERT tokenizer. These are the different targets that we have, training targets and validation targets. What are these targets? The values of toxic, whether it is toxic or not. Then we had already declared the dataset, BERT dataset training. So we have the training dataset, we have the training sampler, then we have the train data loader. So in case of Pytorch, you have to declare different train data loaders as well, which will load the data in different batches based on the batch size you have specified. So in config, you can find this train batch size, and num workers you can also specify. Similarly, just like you specify loaded these three training data sets, you can load the validation data sets. Okay, in this competition, training and validation data set has been given separately, so you can do it like that. Second is that in device, you have to declare it exam.xla underscore device. Okay, and the model is mx.to device. So this is how the device is. In case of GPU, you would have used device equal to CUDA and model equal to a model.to device. In this case, you will use xla.device. If you don't understand this part, it's not an issue. You can leave it as default also, but if you can play with it a bit, it will be good. We have a limited time, so I can't explain it in detail. Then you have to declare the learning rate. So in this case, I'm using a learning rate of 0.4 into 1e minus 5, okay, into xrt underscore world underscore sides. So I had talked about here that in this TPU, it is v3-8. That means it has 8 cores. So we have to multiply. We can multiply the this particular function gives you the number of cores, that is this entire learning rate is going to be multiplied by 8. Why we do that? Because we are supplying it to 8 different cores at one time. We have to calculate the number of training steps. This is the formula that you can use. Why do we calculate this? Because we are also using a scheduler in this case. So in that we have a parameter which we need to pass. Next is the optimizer. We are using AdamW optimizer, and scheduler we are using get linear schedule with warmer. I have also used the lamb optimizer and all different schedulers, but more or less these all give same results. Okay. Now this is the epoch function. You have to use the paraloader equal to pl.parallel loader. What is this used for? We have 8 different cores of the TPU. You have to perform this parallel loading. That is, you have to load the particular data set into 8 different cores yourself. So that is where parallel loader comes in picture. Then you run the training loop function. Okay. Then again you have the parallel loader. You had firstly loaded the training data loader, a training data set to all the cores. Then you load the validation data set to all the cores. Course, and then you obtain the outputs in the targets from the evaluation loop function. Then you save the model. Then you calculate the AUC ROC score. How do you do that? We have kept a condition that if the values of the prediction value is greater than 0.5, the comment is toxic. If it's not greater than 0.5, it's not toxic. Then we calculate it, and at the end of it we again do a warnb.log. Earlier we had done it as loss and loss. We can also log the epochs. Okay, we can also log the ROC AUC score. Now you can't just directly run this function. For running it on one particular core, you can run it simply, but for running it on 8 cores simultaneously, you have to use a special spawn function. Spawn function uses internally a map function. So what is the entire purpose of this is to put it everything simultaneously on 8 different cores. Okay, so it creates multiple copies of the computation graphs. As I told you that the particular code is first made into a computation graph, then it goes into TPU machine code. Okay, so it makes multiple copies of the computation graph, and to make those copies, map function is used. Okay, so now we are going to run this. Don't worry about these warnings. Whenever running TPUs, it causes lots of warnings because you're not using a GPU. You can see won't be currently logged in as Ishan Dutta. Yeah, one important thing. Earlier I had used group_XLA. Group equal to XLA. What happens is, since we are putting the dataset that we have on 8 cores simultaneously, so the won't_be log is going to be generated 8 times. Okay, that is for 8 different per core you're going to get a graph, but we also want to see what is the average of all these graphs. Okay, when I demonstrate the dashboard, it will be more clear to you. So to do that, we have to pass this special argument group, and it need not be XLA. You can write it A B C D, anything you want. Okay, XLA just sounds cool. So this is loading. Okay, you can see the yeah, it might start anytime. So you can see that 8, you can find such 8 texts. So what is there? Good resonance 3, major yoga 2. Okay, these are some funny cool names that won't be provided. So for 8 different cores, these are 8 different pages that you can run, pages that you can get. The main remains at the project page. So you can just click on this project page and go over here. So this is your main won't be dashboard. Okay, you can see that the we are at the group XLA. Okay, so if I tap on it, you can see 8 different cores. So this is what you can see, that the loss has already started calculating. Okay, as I said that it is happening in 8 different cores. So these are all the 8 different cores that's happening. You can see track all the 8 different cores live. Let's track just one of these for now. See, this model is currently training. Okay, and at the same time, this is going to get updated here. So you can see over here. Okay, it has not yet started. No worries. Yeah, it has just begun. The first batch has begun. Yeah, now it has started. So every per batch index 10, I had asked to print the loss. What was the first loss? Okay, so we are beginning at 0.67. Let's see how far we can go. You can just come to this page and you can see it live now. Okay, you can see that this particular line that you are seeing, the darkened one, is actually the average. You see it changed. Okay, so it is actually changing live with respect to the training that is going on. So, and this is the mean of it. You can see sigma and all values are given over here. Let this train. Okay, you can see this value is will keep on getting changed. I have already, yeah, let it train. It will take some time. I have already trained a different one. Let me show that to you to speed up things. See, this was on the same data set. Okay, everything was same, just the run was complete for 2 epochs. To save time, I'm going to show this to you. So the ROC AUC score, you can see that for the first epoch we got around 0.96. For the second we got around 0.98. Okay, this is the epoch that was logged to 1B. For 0th epoch, first epoch, you can see the loss function. This is amazing thing. So this is how you can see the loss function. Okay, now you say that what is the use of it. Let's just edit the panel. Okay, say you have to understand that whether the training was stable or not. You can tap the smoothing and you can extend it to the maximum. Okay, you can see that you have got a very nice linear reducing line that says that okay, the loss function has decreased steadily. That is what is required. You can also to different types of grouping. So since it was on 8 cores, this particular dark line, it is actually showing the loss as an average of all the 8 cores. Okay, we can change this aggregate to median, we can change the aggregate to minimum. Okay, so what was the minimum loss for all these 8 cores, what was the maximum loss for all these 8 cores? You can also change the range. Okay, so this is the min max range that you can see above and below, maximum and minimum. You can change this to standard deviation, you can change this to standard error, you can remove it completely, or you can have it as samples. Let it remain as it is. I can also change the font size that is over there. You can change the position of the legend. Okay, and a lot more. Not only that, okay, you can also see the system metrics. If you know about operating systems, you know what are processes. Okay, so process memory, how it was reduced. Okay, process memory, it was in use, how much. You can also track the actual system memory utilization, the CPU utilization. Also you can see it first it was increased, then it dropped off, then it again increased and dropped off. The TPU utilization is currently not supported by Pytorch itself, it is by TensorFlow. So if you run this code in TensorFlow, it will show you a similar type of graph for TPUs. And if you run it in GPUs also, you can see a similar kind of GPU utilization graph as well. Okay, so these are super helpful for you, and these are being generated live, okay, while the model is training. So if you have made some changes, say you have used mixed precision, you can actually see whether the utilization is increasing or not, whether the code is taking lesser space or not, everything in real time. So this was the group XLA. You can actually also see core wise. Okay, so this is the first core. This is how the losses decrease in the first core, and similarly like that. You can also track the system metrics similarly. You can also have the logs and generate the files. This is what the overview of a particular dashboard looks like. See, this is what the overview looks like. You can either have it as private, only you can see it, and you can also have it as public. The best thing about 1B is for academic experiments and all, it is completely free. Okay, you don't need to pay for this software. It is all available for free. It's still training, so you can see that the loss is steadily decreasing and a number of system metrics are already visible. Fine. So that was pretty much about it. We can keep this training. It goes around 0.98 of AUC ROC score. We are going to get it. And if you make an inference kernel, this will give you somewhere around 0.91 to 0.93 in the original leaderboard. Okay. So that was it from my side. Arshpreet, now we can have the Q&A, I believe. And yeah, one thing that I wanted to add over here, that's that if you just tap on here, you can also see the utilization here itself. So the weights and biases, it's in real time. But in Kaggle, if you want to see it, you just tap on it, you can see 24% of the CPU is being used out of 16 GB, 13 GB RAM is used. And in the TPU, 12% or 13% we had talked about is the matrix multiplication unit. So 13% of this is occupied and idle time is 23%. Okay, let me just quickly explain what idle time is. It's pretty simple. Ashpreet, sorry for taking couple of more minutes. I just want to,
No issues with
explain
that.
everything perfectly. It will take 2 more minutes.
Sure.
See, if you all know the concept of operating systems, you know what idle time is, but I want to explain it to the people who don't know what idle time actually means. So whenever you are writing a code, okay, whenever you write a code, it is actually in the form of a process. So this is your, this is particularly a particular process which we call. So this is the code that we actually have. Then we have a static variables and global variables that you use. Then it is divided into two different parts. One is the heap, that is for dynamic memory allocation. One is the stack, that is for the function calls. This entire thing is called as a process. Okay, now this code that is running, it is actually a process. Let's say this is called as process P1, the TPU code that we are running now. So whenever a process runs, it needs a number of outputs and inputs, okay, from the model or in general. And secondly, it needs a hardware to run on. Okay, so for example, say CPU or GPU. So processes take two types of times. One can be the IO time, okay, that is the input output time, and second is the burst time or CPU time. Okay, in this case, since we are using a TPU, we are talking about the TPU time. Okay, so what happens is, let's say we started the process P1, that is we started running this code at time t equal to 0 seconds. Okay, and it run for 10 seconds. Now after 10 seconds, this particular code needs some inputs from the model, okay, something that is being calculated, and it needs some inputs from the model itself, or it needs some inputs from the user that you need to put out. So this goes, this is particularly in the TPU. Okay, this process needs to go to the IO mode. Okay, that is input output mode. And till the time it is in IO mode, let's say for 5 seconds it needs to complete its IO. So from 10th to the 15th second, the TPU is idle. Okay, so no work is happening over here. After again 5 seconds, the process, that is our particular code, returns back to the TPU, and we return it. Let's say it takes a total of 20 seconds to execute this particular code. 10 seconds has already been executed. You can add 10 seconds more over here, and 25. Okay, so at time t equal to 25 seconds, this particular code completes its execution. But as you can see, because of the 5-second input output that it required, there was no other process to be going in the TPU. Okay, so that these 5 seconds is the idle time, that is no data is being passed to the TPU in this time. That is what the idle time. So 45% of the time is idle over here. You can also see high idle time indicates that the TPU is waiting for the data. That's it. And yeah, first epoch AUC we already have 0.97, and it's being logged in the uh, upon B itself. Yeah, and Arshpreet, now we can have the Q&A.
Sure. Thank you so much, Ishan. That was a really interesting session, and like you explained all the code and the concept so well, and like the notebook is also so brilliantly made. I'm sure the audience enjoyed it. So if you guys have any questions, you can surely ask in the YouTube live chat, and Ishan would be happy to answer.
Yeah, are there any questions?
Um, let's see.
Or was my explanation so OP? I think everyone is writing OP in the chat. Or explanation
Maybe.
was so
Yeah, it's
fantabulous
just
that I think
excellent
people
session.
don't have
Thanks
really
a lot.
questions. So is this not complete models? No predictions yet. No, no. I got this is the complete model. You can see that the outputs, this loss is being calculated on the predictions. If you make the inference notebook, you can find the inference notebook in Kaggle itself. So if you also run it, it can also be submitted to the live Kaggle competition. I believe I have made submissions as well. Yeah, around 0.89, 0.91, 0.99. Okay, these scores were going on somewhere around that. So you can submit it. The predictions are very well being done. Yeah,
Um,
thank you everyone for joining in.
I I think like if you don't have any questions, maybe you can like you have your own live data science mentorship sessions. But like, do you want to share some of those tips for our audience?
See, the code and all I have shared. Okay, since we are talking about Kaggle, one tip,
Mhm.
important tip is that most many of these Kaggle competitions are annual. Okay, as I talked about this jigsaw, right? So if you just type in jigsaw over here and you go to competitions, you can see that three different competitions similarly on toxic comment are there. So what most people do is to get better ranks, they actually check what was the solutions, the top solutions of the previous competitions. So say this year if a toxic comment classification goes on, so you go to the discussion tab and you can find out the top solutions and you can try to implement these over there. Okay, so this is one of the best approaches that can ever use for Kaggle. And other than that, you can use papers with code to understand about different SOTA architectures and all that we have. And that will be pretty much it. And other than that, for my sessions, in case of hackathons, yeah, we have it. Roadmap, I think it will be pretty basic for this session. If you want to get hired for jobs, and you can see that I have done a number of internships and all. One thing that has always helped me was LinkedIn. Okay, so most of these opportunities I tried to bag through LinkedIn itself or through networking. So try to improve your network a lot. Okay, And how can you do that? Connect with good people, ask good questions. Okay, asking good questions is super important. Like for example, instead of sharing an invite to someone, say for a referral or something like that, saying just that, hey, can you tell me how to start about with data science? Okay, a simple question. Asking this, people usually get irritated because most people, if they have a number of followers of in any of these companies, they get these questions a lot. So what you can do is make your questions a bit more specific. For example, you can say that, hello Ishan, that I have already learned about lists, tuples, and I know pretty much about TensorFlow in Python, but how do I level up after this? So when you show that you already have something and you want to improve on it, most people are going to reply. That is why I was able to build some really good connections. And even Arshpreet, I got to know from LinkedIn itself. Okay, so most very nice people are there over LinkedIn. It's just how you ask for help. If you do it the right way, you can get referrals to any company. If you do it the right way, you can get mentors, anyone.
Yeah, yeah. Thank you so much, Ishan, for these amazing tips. And I'm sure the audience loved the session today. So the link to the notebook would be shared in the Telegram group. So make sure you all join it. Yeah, thank
And
you so
if
much, Ishan.
anyone has any further questions, feel free to reach out to me. I will ask Ashpreet to share my LinkedIn ID as well, or put it in the description of
Yeah,
this
I'll
YouTube
just
video. Yeah. So
put
my
it in the.
messages, my messages are actually open. So even without sending a connection request, you can drop in a message.
Great. So yeah, thank you so much, Ishan, for uh, coming here today. And yeah, thank you everyone for joining in. Goodbye. Stay safe. Bye.
Thank you.